Good afternoon. This file contains the pre-lecture notes for class on Tuesday, August 27th, 2013. The relevant reading for these slides can be found in the Carey textbook, edition 8, sections 1.1 through 1.10. You will notice that the takeaways from this lecture include several concepts that you may recall from general chemistry. This is because the first week of class in organic is devoted to ensuring you have a firm grasp of basic general chemistry concepts relevant to organic. Today we will focus on the octet rule, formal charge, resonance hybrids, bond dipoles, and constitution. Much of this semester will focus on the relationship between the structure of an organic chemistry molecule and its reactivity, so be sure that you understand how to use the octet rule to draw a Lewis structure, calculate the formal charge of a molecule, identify bond dipoles, and draw all resonance contributors of a resonance hybrid. So, to begin, recall from general chemistry that atoms are composed of a nucleus and surrounding electrons. Within the nucleus are protons of positive charge and relatively large mass, and neutrons of equal mass with no charge. Electrons of negative charge and much smaller mass orbit the nucleus. Classically, it was believed that the electrons circled the nucleus in circular or elliptical orbits, much like planets do a star. However, in the late 1920s, Schrödinger calculated the precise energy of electrons in molecules using wave equations. The results of these calculations revealed that electrons do not orbit the nucleus like planets do a star, but instead orbit in three-dimensional spaces of fixed shape. Schrödinger determined that the equation, called a wave function, that describes the energy of an electron has a specific value, and that these values determine the probability with which a scientist can find an electron in 3D space. Importantly, each wave function corresponds to very specific 3D shapes, which we call orbitals. Here you can see the probability space of finding an electron in a 1s orbital that roughly resembles the shape of a sphere. An electron in such an energy state can be found in this spherical region roughly 95% of the time. Each orbital is identified by a unique set of 4 quantum numbers. In this course, we are primarily interested in the principal quantum number, n, and the angular momentum quantum number, L. The principal quantum number gives us the energy level of the orbital, and the angular momentum quantum number tells us the shape of that orbital. For this semester, we will focus on s and p atomic orbitals and the resultant molecular orbitals. S orbitals are roughly in the shape of a sphere, and the size of the sphere increases as the principal quantum number increases. S orbitals contain n+1 nodal surfaces, which are defined as a region of space that electrons cannot be found. Here on this slide, we can see illustrations of 1s, 2s, and 3s orbitals. Notice that the number of nodal planes, indicated as the surface boundary between colors in each diagram, increases as n, the principal quantum number, also increases. For a very good simulation of the shapes of different orbitals and their nodal planes, see the URL link at the bottom of the screen. Recall that the Pauli exclusion principle states that no two electrons can have the same set of quantum numbers. The consequence of this is that only 2 electrons and no more can occupy any given atomic and also molecular orbital, regardless of its shape. P orbitals are roughly in the shape of hamburger buns or dumbbells and only exist for energy levels of 2 and above. At each energy level, there are 3 degenerate p orbitals. Degenerate means that each orbital is of exactly the same energy level and shape. However, the 3 orbitals are oriented orthogonal to one another in space. We refer to these as the px, py, and pz orbitals to distinguish between them. To this point, we've focused on the structure and electrons of simple atomic orbitals. But how do these relate to chemical bonding? We will rely primarily on molecular orbital theory to explain chemical bonding this semester. However, in this first week, it's helpful to review the Lewis model of chemical bonding to help you better learn molecular orbital theory when we come to it. Prior to Schrödinger's solutions of the wave equations, Lewis proposed that atoms bonded in a manner that maximized the stability of their electron configurations. At the time, the most stable configurations were believed to be those of the noble gases, Thus, maximum stability resulted when an atom was isoelectronic, which means it has the same electron configuration of a noble gas. Thus, using the knowledge at the time, Lewis proposed that molecules formed covalent bonds with each other by sharing the electrons in their highest energy levels, also known as valence electrons. According to the Lewis model, two hydrogen atoms can form a covalent bond by sharing the single electron in their outer valence shells to achieve the electron configuration of the noble gas helium. You can see down here in the Lewis structure that each hydrogen, the hydrogen on the left and the hydrogen on the right, have two electrons now shared between them in their outer shells. Similarly, fluorine atoms, each with 7 valence electrons, can share a single electron to achieve the electron configuration of the noble gas neon. Once again, notice in the Lewis structure, the fluorine on the left has 8 electrons around it, as does the fluorine on the right, with 2 shared between them. A consequence of the Lewis model is the octet rule, which states that atoms will form covalent bonds to achieve a state in which each atom in the bond has 8 valence electrons surrounding it. This is because all noble gases except helium contain 8 valence electrons. In this course, you will find that the octet rule is the most useful in cases involving covalent bonds to carbon, nitrogen, oxygen, and fluorine. For example, one carbon atom will bond with 4 fluorine atoms to form the molecule CF4, carbon tetrafluoride, written here at the bottom left with all electrons indicated. Notice that the carbon, as well as each fluorine, have 8 valence electrons surrounding them, thus satisfying the octet rule and Lewis's theory of stability. On the right, I've drawn the Lewis structure, which replaces each pair of electrons in a covalent bond with a straight line and leaves all lone pair electrons illustrated with dots. At this point in the semester, it's a good idea to practice drawing Lewis structures in the practice homework problems and the online homework to ensure you can easily draw molecular compounds based on the Lewis model of chemical bonding. Recall that electrons orbit the nucleus of an atom because of the mutual attraction and repulsion between the equal and oppositely charged protons and electrons. Lewis diagrams show electrons as shared in covalent bonds as if the electrons spent equal amounts of time between each of the nuclei in the bond. Electronegativity is a quantitative measurement of an element's ability to attract electrons towards its nucleus when bonded to another element. Electronegative elements attract electrons and electropositive elements release electrons. This table from your textbook includes the Pauling scale of electronegativity. The higher the value, the more electronegative an element is. Notice that electronegativity generally increases as atomic number increases, but decreases as the principal quantum number increases. Importantly, electronegativity tells us that the shared electrons between two atoms in a covalent bond may not necessarily spend equal amounts of time with each nucleus. When two elements bond together, the difference in electronegativity between the atoms determines the polarity of the bond. Nonpolar bonds, like those shown here, contain atoms bonded together with equal electronegativity. Thus, the electrons are shared with equal lengths of time between the two nuclei. In bonds that contain atoms which differ in electronegativity, dipoles are created, which result in polar molecules. Dipoles are bonds in which the electrons are not equally distributed spatially between the two bonded atoms. In a dipole, the electrons are more heavily distributed around the most electronegative of the two atoms in the shared bond. This creates a partial, not full, negative charge on the more electronegative atom and a partial, again, not full, positive charge on the more electropositive atom. Note that we indicate partial charges with a small Greek delta symbol drawn over the atomic symbol in the Lewis structure. Here a delta negative indicating a partial negative charge, here a delta positive indicating a partial positive charge. The dipole is indicated with an arrow pointing toward the more electronegative of the two atoms and the tail aligned with the more electropositive of the two atoms. Using the table on the previous slide, we can see that fluorine is more electronegative than hydrogen, thus the dipole points the arrow in the direction of the fluorine with the tail aligned with the hydrogen atom. Throughout your book, you will see electrostatic potential maps that will help you identify dipoles. These maps show us the charge density around each atom in a molecule. Red indicates partial negative charges, and blue indicates partial positive charges. In this diagram, see how the red portion of the molecule overlays the electronegative fluorine atom, and the blue overlays the electronegative hydrogen atom. The Lewis structure in the center shows the delta positive near the hydrogen atom, which corresponds to the blue surface down here in the electrostatic potential map, and also in the transparent surface over here on the right, showing the ball and stick model beneath the electrostatic potential map. Remember, red indicates a partial negative charge, blue indicates a partial positive charge. Note that dipoles are a result of the difference between electronegativity in two atoms. In HF, H is electropositive compared to fluorine. However, here in HLI, we see that H is electronegative when compared to lithium. Remember to use the color keys to help you determine the charge distribution for molecules that are new to you. Again, the red color in the electrostatic potential map shows us that there's a partial negative charge on the hydrogen in HLI. The blue shows us that there's a partial positive charge on the Li in HLI. To this point, we have only discussed partial charges within molecules resultant from dipoles. Partial charges help us determine the relative electron density in a molecule, however, they are not full charges. Partial charges are found on atoms that bear no charge. To determine if an atom in a molecule bears a full charge, you must calculate the formal charge for each atom. We do this by comparing the number of electrons surrounding an atom in a molecule relative to the number of electrons found in the neutral, unbound element. Formal charges are indicated with a plus sign or minus sign written next to the atomic symbol in a Lewis structure. The formula for calculating formal charge is as follows. Formal charge is equal to the group number in the periodic table minus the electron count. You will have to conduct an electron count each time you want to calculate a formal charge for each atom within a molecule. The electron count is equal to the number of unshared electrons around the atom plus 1/2 the number of shared electrons in the atom. So let's practice using nitric acid. Okay. We'll calculate the formal charge for each atom in this Lewis structure, starting with the hydrogen atom. Hydrogen has 0 unshared electrons in this Lewis structure. Hydrogen shares 2 electrons with the oxygen atom. And we know that hydrogen is a group 1 element. So let's conduct the electron count. 0 unshared electrons plus 1/2 the 2 shared electrons equals 1. Thus, the formal charge is the group number, 1, minus the electron count, 1, which equals 0. The formal charge on the hydrogen atom in nitric acid is 0. Note, this hydrogen atom still has a partial positive charge due to the fact that it's in a bond together with oxygen, which is much more electronegative than hydrogen. Now let's look at the O. Oxygen has 4 unshared electrons in this Lewis diagram. Oxygen is sharing 4 electrons in 2 covalent bonds, 1 bond to the hydrogen and 1 bond to the nitrogen. We know that oxygen is a group 6 element from looking at the periodic table, so let's do the electron count. 4 unshared electrons plus 1/2 of the 4 shared electrons gives us 6. To calculate the formal charge, we take 6, the group number, subtract the electron count of 6, which gives us 0. This oxygen in nitric acid has a formal charge of 0. On your own, it would be good practice prior to coming to class to calculate the formal charges for each of the other oxygens in nitric acid as well as the nitrogen. Remember, you must calculate the formal charge for every atom within a molecule to accurately draw the Lewis structure. Understanding how to draw Lewis structures and to calculate formal charges is important because it forms the basis of our understanding of molecular constitution or connectivity. Constitution refers to how atoms are connected together in a molecule. Understanding constitution is important because molecules that have the same molecular formula may differ in connectivity. Such molecules are referred to as isomers. Specifically, molecules that have the exact same atoms bonded together in different patterns are referred to as constitutional or structural isomers. On the next slide, we can see two examples of this. Ethanol and dimethyl ether each have molecular formulas of C2H6O, but the atoms in each of the molecules are connected differently to one another. So who cares? Why is this important? Remember earlier I said that organic chemistry is about understanding the relationship between the structure of a molecule and the physical and chemical properties of that molecule. Note the differences here on this slide between ethanol and dimethyl ether. By knowing the structure of a molecule, we can predict its effects on people and the environment or how it will behave in a chemical reaction. Because it's tedious to draw out all of the lines in a Lewis structure, organic chemists often use condensed structural formulas. These formulas omit all of the lines that are bonded to one another directly in the Lewis formula. Be careful when you read condensed formulas, as atoms that are placed next to each other are not necessarily bonded to one another. For example, at the bottom right in these diagrams, it's implied that the carbons are all bonded to one another, but that the hydrogens are not bonded to each and every carbon. Usually in condensed formulas, atoms written next to the right of a carbon are bonded to that carbon. It is then implied that the next carbon in line is also bonded to the closest carbon to its left. So if we look down here at this condensed formula, this carbon is bonded to this carbon as well as this carbon. These three hydrogens are bonded to the carbon on the left, this single hydrogen is bonded to the carbon on the left, and these three hydrogens are bonded to the carbon on the left. Note that the hydrogens are not bonded to each and every carbon in the condensed formula. Importantly, such formulas give us more information about connectivity information than the molecular formula does alone. Because organic chemists are lazier than most chemists, they often find that even drawing out condensed formulas is too much work. To simplify things, we use the bond line formula, which omits all C and H symbols except in cases where H is bonded to an atom other than C. We refer to any atom other than carbon or hydrogen as a heteroatom in organic chemistry. In bond line diagrams, carbon atoms are implied at the end of lines that have no heteroatom and at every bend or kink in the backbone. Hydrogen atoms are not drawn but are implied consistent with the octet rule. For example, note down here in these formulas we get even more structural information as the overall shape of the molecule is implied by the zigzagging backbone of the molecule. To decode these, remember, a carbon atom is implied at the end of every line that does not have a heteroatom, as well as at every bend or kink in the backbone. Hydrogen atoms are also implied consistent with the octet rule. Thus, if there's one carbon atom at the end of this line bonded to a second carbon, this carbon atom must have three invisible hydrogens attached to it in order to complete its octet. Up here, this carbon, implied by the bend in the line, is bonded to two additional carbons, indicated by the lines coming off of it. It must therefore have two implied hydrogens to complete its octet, which are not drawn. Notice down here, in this formula, a carbon is once again implied at the end of a line without a heteroatom, but no carbon is implied over here because a heteroatom oxygen is drawn at the end of the line. Organic chemists often make use of VSEPR, or valence shell electron repulsion theory, to help explain the shape or structure of organic molecules. Recall that VSEPR theory tells us that the most stable shape of a molecule is the one that includes the maximum separation of electrons in each orbital. Using VSEPR theory, we can predict that the shape of water is bent or tetrahedral if we can include both electron pairs in our overall shape. Note that the bond angle here is less than the predicted 109.5 degree angle of a true tetrahedron because the lone pairs, which occupy a larger volume, repel the OH bonds and push them closer together. On the next slide, we can see that ammonia has the predicted pyramidal shape. The molecule is also tetrahedral, as is water, when lone pairs are considered. Note that the single lone pair does not exert much repulsive force as the two lone pairs in water does, and the H and H bond angles are thus larger than the H-OH angle seen in water. Formaldehyde, which contains 3 atoms around the central carbon atom, has trigonal planar geometry given that all orbitals repel each other with roughly the same force. Here notice that we've drawn the Lewis structure on the bottom right to be consistent with the trigonal planar geometry of the molecular model shown on the left. Remember, because we are concerned with structure in organic chemistry, it's important that we convey the most accurate structural information in our diagrams. Traditional Lewis diagrams fail to do this, and you should practice on drawing Lewis diagrams and bond line diagrams in a way that most accurately depicts the overall shape of a molecule. This will be critically important as you learn to differentiate between organic reaction mechanisms later in the semester. The final general chemistry concept for this lecture concerns resonance. Resonance considers the delocalization of electrons over multiple bonds in a molecule that minimize energy and improve molecular stability. A resonance hybrid is the aggregate probability of finding the electron across multiple bonds. The possibility of localizing electrons in different places in a molecule gives rise to multiple resonance contributors. Each contributor depicts a unique charge density for the same molecule. Note that contributors are not different molecules. Although we will draw individual diagrams for each resonance contributor of a hybrid, remember that they are all showing the same molecule. One way to think of this is that the contributors are like pictures of the molecule with its electrons located at different bonds or on different atoms at different points in time. Take, for example, ozone. This Lewis structure over on the right indicates that one oxygen contains 2 lone pairs, one oxygen contains a lone pair and a formal positive charge, and one oxygen contains 3 lone pairs and a formal negative charge. Moreover, we have a double bond on the left side and a single bond on the right. Importantly, this Lewis diagram does not match the empirical data on the structure or charge density of ozone. Based on this diagram alone, we would expect one short bond and one long bond in the molecule. In the laboratory, however, we have seen that all bonds are of equal length. Thus, this Lewis diagram does not correctly show either charge density or structure. When we look at an electrostatic potential map, we can see that the resonance distribution of electrons explains the fact that both bonds are observed to have the same bond length. The electrons are equally distributed across the terminal oxygens, as indicated by the similarity in color in the electrostatic potential map. To communicate this, we draw 2 resonance contributors to show the equal distribution. We indicate the relationship between the 2 contributors by linking them with the double-headed arrow. Note that this is not an equilibrium arrow. It tells the reader that these 2 drawings are just different pictures of the same resonance hybrid. On the left, the resonance contributor is shown to bear the negative charge on the oxygen on the right, drawn in black. And on the right, the resonance contributor shows the negative charge on the oxygen on the left, drawn in red. So, how do we write resonance contributors? First, all contributors must have the same connectivity and the same net charge. If they differ in connectivity, you have constitutional or structural isomers. You do not have resonance contributors. Notice in this diagram that I've drawn down below, I've drawn isomers because the connectivity is different. The diagram on the left shows a hydrogen atom bonded to a nitrogen and another hydrogen atom. The diagram on the right shows the nitrogen bonded to only one hydrogen atom. That hydrogen atom that was there on the left has moved over to the oxygen atom on the right. Thus, these 2 structures are not resonance contributors. They are instead structural isomers. The second rule is that each contributing resonance structure must have the same number of electrons and the same net charge in order to be a resonance contributor to the resonance hybrid. If they differ, you have gained or lost electrons on some of the atoms in your drawings. Notice in the diagram below, all three of these structures indicate resonance contributors of the same resonance hybrid. The connectivity is the same in each structure, and the charge is the same in each structure. Note, if you have multiple contributors, the major contributor follows these rules. First, the major contributor obeys the octet rule. Second, it possesses the most covalent bonds. Third, it places negative charges on the most electronegative atom in the structure. And fourth, it places positive charges on the least electronegative, or alternatively, the most electropositive atom in the molecule. Note the two resonance contributors of the structure of formaldehyde drawn here on the right. The contributor on the left has 4 covalent bonds drawn. The contributor on the right has only 3 covalent bonds drawn. Okay. The contributor on the left obeys the octet rule. The contributor on the right does not obey the octet rule. Note that only the oxygen contains 8 electrons around it. As drawn here, the carbon is missing a pair of electrons and thus does not satisfy the octet rule. Based on these two criteria alone, we can determine that the major resonance contributor for the resonance hybrid of formaldehyde is the structure on the left. Always assume that you can draw resonance contributors of a resonance hybrid when you have a double bond between a carbon and any heteroatom, when you have a lone electron or a lone electron pair adjacent to a double bond, as seen on the right here. Notice that the double bond is adjacent to a lone pair of electrons indicated on the terminal carbon in this structure. Alternatively, assume that resonance is possible when you have a lone positive charge adjacent to a double bond. Down here, notice that the double bond is once again adjacent to a positive charge. With that, that's all for today's pre-lecture. Be sure to review the relevant sections in your textbooks and come prepared to apply what you have learned in class on Tuesday.